your lessons on series resistive circuits, you learned about current, voltage, resistance, and power in a DC circuit. This will help you to understand troubleshooting these same circuits. What is troubleshooting? It's the process of locating causes of faults or troubles in whatever you're concerned with. In this lesson, we're concerned with troubleshooting DC series resistive circuits. The most common troubles you'll find in these circuits are opens and shorts. So I'll stick to these two troubles. First, let's consider some examples of open. Here are some troubles that could cause an open. This one is a battery with loose connections. Most of the time, a loose connection is the same as no connection, which is the same as an open. Any circuit component with a loose connection opens the circuit and stops current. Another type of trouble that will cause an open is a burned-out component. This is a burned-out resistor. When a resistor gets overheated, its values are changed. But if enough current passes through any resistor, it can be burned completely open like this one. This lamp has a burned-out filament or lighting element, so it's an open also. Here are two other examples of opens: a switch with a loose contact and a broken wire. All of these components could cause an open, and they all give the same results. Now let's consider a very simple series DC circuit. This one just lights a lamp. By opening the switch, the current will stop. This would be an intentional break in the circuit. In this case, it's an intentional open circuit. If a break occurs at any other point along the circuit, we would have an unintentional open circuit. Unwanted opens in this circuit would be broken conductors or a burned-out filament in the lamp. I've shown you several examples of opens. An open means a condition of discontinuity in a circuit, which normally passes a current. Discontinuity is the opposite of continuity. When you have continuity, there's a complete path for current to flow. The circuit is continuous. Discontinuity means this path is broken or open. So by now, you should have a fair understanding of an open. So apply what you've learned to this. It's the first one on your response sheet. You should have written break and discontinuity in either order. Do this one. It's number 2 on your response sheet. You could have answered in many ways. but this is the main idea. The opens I've shown you so far could be found by visual inspection. That is, by simply looking the components over carefully. However, you will encounter opens that cannot be seen. In these, you'll have to use a meter that will detect the symptom that an open gives to this circuit. Here is a circuit to light a lamp. But because of the open resistor, the lamp will not light. Suppose this resistor looked all right from the outside, visual inspection wouldn't help. So how could you tell it was open? You could do this with either a voltmeter or an ohm meter. First, I could connect the voltmeter across the lamp. There would be no voltage present, and the voltmeter would indicate 0 volts. Why? Because of the open resistor. This open will not allow any current flow, so there won't be any voltage dropped across the lamp. That's why it's not lit. So what you'll get across a good component that is in series with an open one is no voltage. Now I'll connect the voltmeter across the resistor. The voltmeter has provided a path for the current to flow. Current will flow from the negative terminal of the battery through the lamp up to the right lead of the voltmeter, then through the voltmeter and to the positive side of the battery. The resistance of the voltmeter is so high that it'll only let a tiny current flow. This current is too small to light the lamp, but the voltmeter will read the battery voltage. In other words, it will read the total voltage in the circuit. The rule is, when your voltmeter is across the open component in a series circuit, you'll read the battery or applied voltage. I'll show you an actual circuit identical to this one. There are 2 batteries which together supply the total voltage in the circuit. I also have a 5-ohm resistor. This resistor is open and connected in series with the lamp. When I connect the unconnected terminal of the lamp back to the other side of the batteries, the circuit is complete. Notice now, even though I have all terminals connected, the lamp does not glow. So with the voltmeter, I'll take measurements across the lamp and the resistor. You record the voltmeter indication as I go. Spaces are provided under number 3 on your response sheet. First, we'll connect the leads across the lamp. The voltage across the lamp is 0 volts. Record that on your sheet. Now I'll move the leads and hook them across the resistor. The voltmeter is now reading 3 volts. Record that. This voltage is the same as the applied voltage. Let's check it. As you can see, the values are the same. So, when you connect a voltmeter across a good component in series with an open one, you get 0 volts. On the other hand, when you connect the voltmeter across an open in a series circuit, the voltmeter will read the applied voltage. And now you complete the 2 sentences under number 3 on your response sheet concerning this circuit. In the first blank, you should have written in something to the effect that the lamp will not light. In the second blank, you should have written in battery or applied voltage. Now that you understand the indication a voltmeter will give for an open and for a good component, let's go a step further and see how an ohm meter will indicate open and good components. I'll use the same circuit we had before. The main thing to remember, of course, is that the power will have to be removed from the circuit. If I had a switch in this circuit, I'd open it. Instead, let's pretend I've disconnected one end of the battery. Now, if I connected my ohm meter across the lamp, I'd read some value of resistance, large or small, depending upon the resistance of the filament. But the point is, there would be a reading. However, an ohm meter across the resistor will read infinite resistance, wouldn't it? So here are the rules. When you connect an ohm meter across an open component, the ohm meter will indicate infinite resistance. When you connect an ohm meter across a good component, the ohm meter will indicate the resistance of that component. So much for that. But how will a broken wire affect the circuit components? Now, here's a circuit quite similar to the one I showed you before. It consists of a battery, a resistor, a broken wire connected between the resistor and lamp with the lower lead of the lamp connected to ground. Since the lower lead of the battery is also connected to ground, this amounts to connecting these 2 leads together, which makes this circuit the same as the previous one. Let's call the open point A. How about the voltage across the resistor in this circuit? It's 0. This voltage is 0 because the open does not allow any current to flow in the circuit. In order to have a voltage across the resistor, there must be current through it. What about the voltage across point A, the open in this circuit? You can see by connecting the voltmeter across this point, it will complete the circuit, which will allow a small current to flow. The resistance of the voltmeter is much greater than that of any other component in the circuit. So, in effect, it will read all of the applied voltage. If you were to connect the voltmeter across the lamp, you would get the same indication as you would across the resistor. Again, the reason for this is the open does not allow current to flow. Keep in mind that you'll only connect a voltmeter across one component at a time. So the rule still applies. When you have an open in the circuit, regardless of whether it's a component or an open wire, by connecting a voltmeter across that open, you'll read the applied voltage. You might say that when you find your applied voltage within the circuit, you've found your open. Voltage across good components in series with the open will be 0. You have a circuit like this one under number 4 on your response sheet. Complete all of item 4 on your sheet. You should have answered that the light would not be lit and that meter 1 would read 0 volts while meter number 2 would read the battery voltage. Electrically, this circuit is identical to and the resistor. Now I'll break the circuit and see what happens. By opening the lead between the resistor and the lamp went out. So your response should have been something to the effect that the lamp will not light. I've given you quite a bit on open circuits. Their symptoms should be pretty clear in your mind. I'll talk about opens a little more in the latter part of this lesson. But now let's go to another trouble that is common in electrical circuits, the subject of shorts. You have seen how an open stops current flow. Shorts, on the other hand, produce just the opposite effect. A short across a series component produces a larger than normal current flow. Let me show you some examples of shorts. We'll use this component as our first example of a short. Connecting the two terminals of a resistor together by a piece of wire, we'll short out the resistor, and the value of the resistor will not be felt in the circuit. Connecting the two leads of a battery together will cause a short and produce a high current. If this current is allowed to flow for too long a time, it will completely discharge the battery. Another example of a short is two bare wires in a circuit touching each other. Also, improper wiring could cause a short. Here, both leads of the battery are connected to the same terminal of a resistor. This amounts to connecting the leads together and again could damage the battery. So, a power source needs some resistance in the circuit. This resistance will regulate the current and keep it down to a normal value. Shorting across the resistor will eliminate its effect and there will be no regulation. This will allow a very large current to flow in the circuit. A short amounts to connecting two conductors of a circuit through a very low resistance. In this case, the two conductors are the wires connected from the battery terminals to the terminals of the resistor. The low resistance is the wire that connects the terminals of the resistors together. And now you do this one. It's listed as number 5 on your response sheet. You should have completed this statement, so it would read, a short is a connection of two conductors of a circuit through a very low resistance. Let me review the main points you've learned about shorts so far. First, you learned that a short is a low resistance path connecting two conductors of a circuit. Then you learned that if a resistor connected across the voltage source was shorted, the circuit current would become much greater than normal. Now let's take this idea a step further by analyzing what would happen when another circuit component is connected in series with a shorted one. This circuit is designed to light a lamp. Since the resistance of the lamp is normally low, a resistor is connected in series with it to control or limit the amount of current flowing through the lamp. Now, if the resistor you see was shorted out, the total circuit resistance would decrease and the current would increase. This increase in current would cause the lamp to become much brighter. If the battery voltage was high enough, the current could increase to a point where it could destroy the lamp unless the circuit is properly fused. You learned in an earlier lesson that most circuits are protected against excessive current by the use of a fuse. Remember, the fuse is designed to open the circuit when the current exceeds the rated values for the components in the circuit. This circuit is the same as the one I explained before. It has a 5-ohm resistor connected in series with a small lamp. Since the resistor is limiting the current, the brightness of the lamp is less than what it could be. But we'll call this brightness normal for the lamp. Now I'll short out this resistor. Note the effect on the lamp. Notice that the brightness of the lamp is much greater now than it was before I shorted the resistor. Now we can make this statement. When a good component in series with another good component becomes shorted, the circuit current will increase. This increase in current will not flow through the shorted circuit component, but it will flow through the good component. And now do number 6 on your response sheet. In the first blank, you should have recorded brighter. To explain your answer, you should have something to the effect that the increase in current caused the lamp to burn brighter. In this circuit, I have 3 resistors connected in series. If I short out one of them, the current will increase. With this short across R3, it's no longer in the circuit, and the total resistance is made up of R1 and R2, which is less than all three resistors combined. This accounts for the increase in total current. Now, if I short out R2, the current would increase even more. With R2 and R3 shorted, the total resistance in this circuit is made up of R1 only. So regardless of the number of components you have in a series circuit, shorting out one of them will cause the current in the circuit to increase. Shorting out another component will cause the current to increase even more. In other words, as you short out components, you decrease the total resistance in the circuit and increase the current. Now, do number 7 on your response sheet. Your response should be, current will increase. By now you should be well grounded on what readings you'll get by connecting a voltmeter across an open or a shorted component. You'll have to use these indications to tell whether the component has an open or is shorted. And now let's analyze this circuit. When the voltmeter is connected across R1, it indicates 55 volts. When the meter is connected across L1, it indicates 35 volts. When the voltmeter is connected across R2, it indicates 0 volts. Now, what trouble or troubles would there have to be in this circuit to give these indications? Think about it for a moment. Since we have a voltage across R1 and L1, we know they are neither open nor shorted. But how about R2? If it was open, we'd read the applied voltage and would not have any voltage indicated across R1 or L1. There cannot be any voltage across a short, since a short is a very low resistance. Therefore, R2 is shorted. Then in this circuit, we have one short and no open components. Do this one. It's listed as number 8 on your response sheet. In the first blank, you should have none or something to the effect that there are no opens in the circuit. In the second blank, you should have R1. Look at this problem circuit for a moment. Here's a circuit that has a lamp with 50 volts across it, but the lamp is not lit. R1 and R2 are connected in series with the lamp, and neither resistor has any voltage across it. What trouble or troubles are in this circuit? It may appear to you, at first glance, that R1 and R2 are shorted. This is sound thinking, since there is no voltage across these two resistors. But what if there is an open some other place in the circuit? Remember, an open in a series circuit stops current flow. With no current in this circuit, there could not be any voltage drop across R1 and R2. Then an open could cause no voltage across these resistors. Or, if both resistors were shorted, this would also explain the lack of voltage across them. The only other component we have in the circuit is the lamp, and it's not lit. If R1 and R2 had been shorted, there would be enough current in the circuit to light the lamp, since there are 50 volts across it. So this means that R1 and R2 are not shorted. Since we have 50 volts across the lamp, this also means that R1 and R2 are not open. Had they been open, there would be no voltage across the lamp. So this boils our trouble down to the lamp. Having 50 volts across it and yet not being lit, L1 has to be open. So, with the voltmeter readings as indicated, L1 is open, and R1 and R2 are neither open nor shorted. Now, you try one like this. It's under number 9 on your response sheet. To complete this statement, you should have written L1 after open and none after shorted. This completes your lesson on troubleshooting DC series resistive circuits. Remember, an open stops current flow and a short increases current flow. Your next lesson will be on voltage dividers.